Hey guys, welcome back. So in this video we're going to be going over the derivative of trigonometric functions. So from now on we're going to be learning derivatives of trigonometric functions, not just by themselves but including our chain rule in them, right? So now that we already learned the chain rule, every derivative we're going to start taking from now on is going to have the chain rule in it. And it's okay if you're not completely comfortable with the chain rule from the examples that we've done. We're going to be doing a lot of practice on different types of chain rules with all different types of functions to make sure that we just get it down packed. So let's go ahead and get started. So here we have that we'll be discussing the 6 main trigonometric functions, right? And the 6 main functions are going to be sine, cosine, and tangent, and the other 3 are going to be cosecant, secant, and cotangent, right? So that's sine, cosine, tangent, and cosecant, secant, and cotangent. Those are our 6 main trigonometric functions, right? And now, there's no crazy way of me telling you like, hey, do this and you'll know all the derivatives, but the best thing that I can come up with to help you guys remember the derivative of trigonometric functions is going to be the 3 C's rule. And what that tells you is that the derivative of functions that start with a C, and those being cosine, cosecant, and cotangents, their derivative is negative. So whenever you ask yourself if the derivative that you're taking of this trig function has a negative, you just ask yourself, does it start with a C? So if it does, then it has a negative, and if it doesn't, it doesn't start with a negative. It's as easy as that. So let's go ahead and look at this, right? So the first derivative is going to be cosine, right? The derivative of cosine, which starts with a C, is going to be negative sine of x, right? So we're going to make a relationship here, a little marriage between cosine and sine. So these two are going to be married, okay, when it comes to trig derivatives. And now we're going to have the derivative of cotangent, which also starts with a C, is going to be negative cosecant squared, all right? So the derivative of cotangent is going to be negative cosecant squared. So cotangent and cosecant are married, right? And we're going to see how well they're married in the next derivative when we derive cosecant. So when we derive cosecant, the derivative of that is going to be negative cosecant as well. We're going to have a cosecant as well, and it's going to be with its partner with cotangent, right? So we see that cosecant and cotangent are married. So you guys see out here the derivative of cotangent is negative cosecant squared, and also when you derive cosecant, it's cosecant again, but then it's with its partner, right? So it's with a cotangent next to it. And now we're going to go ahead to the 3 kind of like more boring, they don't really have a rule, they're just some positive derivatives that we have, and we're going to derive sine in the first one here. We're going to derive sine, and as you guys see, a derivative of sine of x is equal to positive cosine, right? So sine doesn't start with a C, so we don't care about it being negative, so the answer is just positive. And once again, sine and cosine here are going to be married, right? And they are married in the 3 C's rules as well, right? So this right here is going to be our 3 C's rule. And then we go to the 5th one, which is going to be the tangent, right? The derivative of tangent is going to be secant squared. So we can discuss a little relationship here. But if you guys used to think about cotangent and tangent as like the same family of functions, but they actually do have something in common here. You guys see how cotangent and tangent, their derivatives are both squared. So there's another relationship that we need to make so we can help ourselves remember these rules, because it is a bunch of rules. You guys already know the power rule, the product rule, the quotient rule, the chain rule, and now we have all these other function rules that we need to memorize, right? So I'm just trying to help you guys out here to make some relationships. And last is going to be secant, but we already said that tangent and secant were married because of this guy right here, because of this example. So the derivative of secant is going to be secant again of x times tangent, because we said that secant and tangent are married, right? So we have secant times its partner tangent. So we have discussed the 3 rules who are negative, which are the 3 C's rule, which are the 3 functions that start with a negative, which are cosine, cotangent, and cosecant, and then we have the other 3, which are just positive functions of sine, tangent, and secant, which neither of them starts with a C. So now let's go ahead and do some practice problems so we can see how these rules can apply. So here in letter A, we're asked to derive the following function, right? We have 2 cosine of x minus 3. Okay, so let's go ahead and derive this right away. So I put my f prime here of x, and now I'm going to have 2. I'm just going to have the constant outside, the coefficient just outside hanging out. So it's going to be 2 times the derivative of cosine. So now, whenever we run into a trig now, the first thing we ask ourselves is, does this function have a c? Does it start with a c? And we tell ourselves, yes. Yes, cosine does start with a c. So our derivative is going to be negative. So we're going to put a parentheses, and automatically we're going to put a negative. And who is cosine married with? Sine. So the derivative of cosine is sine, but negative sine, because it starts with a c. And now we're just going to have to take the derivative of minus 3, which doesn't matter because it's a constant, and we know the derivative of a constant is just 0. So now our last step here is to kind of simplify this a little bit, and we're going to have f prime of x is equal to negative 2 sine of x, right? Which kind of makes the negative and the 2 and put it together. And we're done. We just did a trigonometric derivative using cosine, which was part of the 3c's rule, right? So whenever we have a trig function, we're going to ask yourself, does it start with a c? And let's go ahead and do another derivative here in letter b. So we're given f of x equal to 5x plus 3 sine of 7x. Cool. Let's go ahead and derive this. So now we're given 5x. What was the derivative of 5x? We use the coefficient rule, and it's just going to be 5. So the derivative of 5x is just 5. Done. Boom. Now let's go jump into this other derivative, which is going to be the 3 sine of 7x. The difference between this case and, there's two differences actually, between this letter B and letter A, is that starting with our function, sine of x does not play a part in our 3c's rule, because sine of x does not start with a c, it starts with an s, so therefore the derivative is not negative, so we have a positive derivative, we're good. But now, look at sine of 7x. How is it different from how is it different from cosine of x? If you guys notice, cosine of x is simple, while 7x is a little more complicated, right? So more complicated means a composite function, and a composite function means a chain rule. So here we have a chain rule to do, right? So let's go ahead and derive the outside function, which in this case is just sine of x, right? So we just have sine of x outside, and we're going to go ahead and derive that, which is going to give us cosine, because the derivative of sine is just cosine, and we're going to leave our inside function the same, right? We just leave our inside function the same. So we kind of put our finger over the 7x, we look at the sine of x, we say derivative of sine of x is cosine of x, we leave the inside the same, and now we go ahead and we look, we take our finger away, and we look, 7x. What is the derivative of 7x? And that is 7. So I'm going to go ahead and multiply. I'm going to put this in blue because I'm multiplying now by 7, which is a derivative of the inside. Alright? So here we go back to the whole peeling the onion idea now with trigs, right? And with trigs, I would say it's a little easier to see because you just kind of have the outside function always to the far left. And then we just kind of keep going inside. And you guys will see how, when these get a little harder, how we get it done. So now let's go ahead and clean it up. This 5 here just kind of comes down. And then we're going to join this 3 and this 7, which is going to give us 3 times 7 is 21 cosine of 7x. And we're done. We're good to go. Alright? So now, let's go ahead and do example C, in which we're asked to find the derivative of sine of 5x divided by cosine of 2x. So now here in this example, we're combining a lot of rules together. Right? First of all, we're applying our new learned rules of how to derive trigonometric derivatives. Then we're also going to have to compute a quotient rule, right? A quotient rule because we have two functions dividing. And last, inside of this quotient rule, if you guys notice, the angles here, 5x and 2x, are they're composite functions. They're a little more complex, and we say that it's more complex when it's just anything different than x, right? Anything other than x, right? So 2x is already more complex than x because we have a 2 in front of the x, right? So that's what I mean by it's a little more complex. It's going to be a composite function. So we're going to have to say that we have a chain rule. Okay? So let's go ahead and jump straight into this derivative. And let's set it up first, right? So we know we're going to have something here in the bottom, squared. We're going to need 2 parentheses on top, a big minus in the top, and 2 more parentheses on top. Okay? So how do we start this? If you guys remember, let's go ahead and give these functions 2 colors. The top is going to get blue, the bottom is going to get green. And I like doing this just to keep you guys in check with the formula, right? So the recipe to compute a quotient rule is going to be bottom squared, which in this case is green squared, so cosine of 2x squared, no derivative, just bam, squared. And now we start off, the first parenthesis in the top is going to start off with the derivative of the top, or the derivative of the blue. Which, if we look at the derivative of sine of 5x, we see that we have a composite function because we have a 5x inside of our sine of x, right? So we're just going to start off with the outside. And what is the derivative of sine? Well, first of all, sine does not start with a c, so we're going to go ahead and say that it's a positive derivative, and sine is married to cosine, so the derivative of sine is cosine of 5x. Now, are we done? And we're not, because you guys see this 5 of x still needs to be derived, the inside of that function still needs to be derived, and that is going to be times another 5 right here, times 5. Now for the second parenthesis, it's going to be a lot easier because we just rewrite, we multiply the bottom, so we're going to write the bottom right in there, so cosine of 2x, no derivative, minus the derivative of the bottom, which is going to be, we look at cosine of 2x, right? So first of all, does the function start with a c? Yes, cosine starts with a c, so therefore a derivative is going to be negative. So we're going to have a negative derivative, and who is cosine married to? Sine of x. So it's going to be negative sine of 2x, right? Negative sine of 2x. And now we look inside of our cosine, inside of the cosine of the angle, and we have a 2x, which the derivative of 2x is just 2. So we're going to go ahead and multiply this by 2. Okay? And now here at the end, we're just going to multiply by the top, which is the blue function, which is going to be sine of 5x. And we're kind of going to go into the space of letter D, but it's okay. Letter D won't mind. I asked. Okay? So we already computed our quotient rule using chain rules to take certain parts of the derivatives, right? So now we're seeing how we're using different skills just all at the same time and with no warning. It's just like, boom, derive this, boom, let's do it. So let's go ahead and clean it up, which is kind of the more tedious part, right? So here we're going to go ahead and have this cosine of 5x times 5. Let's put the 5 in the front. So now we're going to have 5 cosine of 5x times cosine of 2x. We can't do anything there. They're different angles. They're just by themselves. They're different cosines. And now you guys are going to see how this negative and this negative here are going to cancel. They're going to just turn into a nice positive. And we're going to have this 2 here. We're going to have it come to the front. So 2 sine of 2x. So we got rid of the negative by joining with a negative from the quotient rule, giving us a plus. And then we're going to have sine of 5x, right? We're good to go there. And now this is going to be all over cosine of 2x all raised to the second power. And we're done, right? So I do know that I'm going a lot faster in the whole chain rule thing, but I'm going to be giving you guys a lot of practice, and I'm going to be going over the solutions a lot of examples to make sure you guys do get a lot of practice and hands-on activity on this, right? Because the more chain rules you do, the more natural it is. Like, there's just no magical thing I can just say to you that you're just like, wow, I'm a pro at chain rule. There's nothing there to be done. Chain rules needs to be done, and you just recognize all these patterns, and just it's gonna be a lot of recognition and just practice, right? So we always see that with trigonometric functions. We derive the outside function, and then we derive the angle. That's always going to be the idea. And if the angle is composed, we go ahead and derive that angle again. But I'll give you guys an example of that. Not right now. But that's the idea with trigs, right? We derive the outside function, and then we derive the inside, right? So it's much easier to see with trigs than to do with functions to the power, because the outside function is just the function itself. There's no like hidden power function here. Okay? So let's go ahead and jump into letter D and see what we can do here. So with letter D, I actually put it here because 1 plus tangent to the second of x is actually an identity, right? And that is actually why I have this box here. I have this box here in which I have 1 plus tangent squared is equal to secant squared. So I'm going to go ahead and change that just so I can use my identities. And because I really want to do something with this problem. And that is that whenever you have a function to a power, in this case tangent squared, or in this case secant squared, right? So secant to a power, what we're going to do is we're going to put that power outside. Even before we start deriving, we're going to put that power outside. Okay, so let's go ahead and rewrite this. We're going to have secant. We're going to have secant of x raised to a power, which is going to be the second power, right? And just take it outside. And here, the reason why I did that and why I took out the power from in there between the function and the x, the reason why I did that was because now it looks a little more, it jumps at you that you have a function inside of another function, right? The whole idea of a composite function just jumps at you because you know that you have a function, the secant x being a function raised to a power. So that's kind of when we recognize that we need to do a chain rule whenever we have something raised to a power or something inside of something else, right? In this case, the baby is going to be secant of x. It's inside its mother function that we have here, the second power. So let's go ahead and do that. Let's go ahead and take the derivative of this. And we're going to start off with the outside function, right? We're going to peel the onion by starting with the outside function, which is going to be, we're going to put our finger over the parentheses, or the bracket in this case, and we're just going to cover the secant of x. And when we do that, right, we just have parentheses to the second power, so we're just going to bring that down. So it's going to be 2 parentheses to the first power, and now we're going to review what we have in the inside, which is secant of x. Now we care about it. And now we go ahead and take the derivative of the inside, right? So the derivative of secant of x, which is a part that ties into our whole trig derivatives, is going to be secant. The derivative of secant is going to be secant of x. And who is secant married to? Tangent. Okay? Tangent. And you guys see here that also 1 plus tangent squared gave you secant squared. And you guys can see that relationship between secant and tangent, right? So if you have any questions or you forget who is married to who, go back to your identities, because those properties are actually in there. And there's a reason for that. But we're not going to get into the crazy mathematical proof and technical stuff. We just want to go with the easy stuff so we can compute all these crazy derivatives, right? So how can I simplify this a little better? I realize that I have one secant of x. Here I have another secant of x. So I'm going to go ahead and have 2 secant of x squared. I can go ahead and put the square here because I'm not about to derive, so I can just put my square there, times tangent of x. Okay? That is going to be my final derivative because I just combined the 2 secants, I multiplied them, and I got secant squared of x times 2, and our tangent of x just kind of came down from here. Okay? So now we went ahead and we computed these derivatives using the trig derivatives, right? The trig rules that we have. So the most important thing to remember about this video is the idea of the 3C's rule, which goes with the 3 negative derivatives. The 3 functions that start with a C have negative derivatives. That is the main thing to take away from here, and then also how to manipulate these derivatives using quotient rules, product rules, chain rules, and just everything that's going to be thrown at you, right? So now let's go ahead and do some more practice problems in which you guys are exposed to different types of scenarios that you have to use the trig rules, the trig derivatives, to solve more derivative problems. So, see you guys next time.